chairman will be Mr. José. I have some reminders to do. The persons who are going to play the paddle tournament, is there anyone here? Okay, so please, you have to take your personal equipment for the visit, because there will be some transport specific to get you at the visit and to take you to the paddle tournament directly. So you don't come to the hotel again. Okay? Also, please be aware that the buses for the visits will leave the door of the hotel at 30 minutes past 2. Everyone who is not at the bus will not take the transport for the visit. So at lunchtime, please do it as quickly as you can. So you should be at the door at 2:30 to get in your line for your bus visit. There will be 4 different buses for different visits. So take your bus to the visit and it will leave at 2:30. Okay? So, Mr. Bio, you take the floor.
Yes. Good morning. I'm José. I am working with Andritz, and I will be your moderator for the last session of the morning, and actually of the day. Are you able to listen my voice in the back? Okay, very good. So the plan was to have 3 presentations in this session, but in the final we end up with only 2. One was moved to another session, and like that I will start presenting the first person that will present. It's Matias Hultgren. He works as a technical manager for mill-wide optimization at Valmet Automation in Pértega. Matias is a Doctor of Science Technology in Process Engineering from the University of Pulp, specialized in control and systems engineering. He has over 10 years of experience in R&D from academia and industry concerning solutions for the modeling, simulation, monitoring, control, and optimization of power plants, pulp and paper processes, and mineral and metallurgical processes. Once we have only 2 presentations, I already told that we don't need to rush that much, and we have extra 5 minutes for your presentations. So please, Matias, go ahead.
Okay. Okay. So, thank you, Chair, for the kind introduction. Can everybody hear me in the back as well? Do I need any additional equipment? That's good. So, good day, everybody. I would also like to, aside from myself, I would like to bring you the greetings from the main author of our paper, Mr. Greg Freilich, from the other side of the Atlantic Ocean, from Valmet, Canada. And I'm going to spend the next 15 to 20 minutes of your valuable time to talk about pulp mill production planning using the Valmet mill-wide optimization solution. This is the brief outline of my presentation. We will start with some background about mill-wide optimization, what we mean by it, why it is needed, in our opinion, in pulp and paper. Then some brief theoretical description. We won't go too deep, but basics about flow sheet optimization, which is the core of the mill-wide approach. As well as some words about the mill-wide optimization platform. Then we will move on to the actual case study, the pulp mill production planning. We will give the background and go through some results. And finally, we will end up with the conclusions of the presentation. So, first section, what do we mean by mill-wide optimization? So, the pulp and paper industry has been leveraging the power of the optimization of local process areas, like individual process areas, like cooking optimization, bleaching optimization, causticizing optimization, and so on. With great success, with documented benefits for yield, throughput, quality, production costs, and so on. So this is very kind of established technology, even though research and development obviously is still going strong, and the local optimization is performed through various kinds of advanced process control solutions. However, what the local optimization of an individual area like bleaching can fail to take into account is that in a pulp mill, for example, that we're talking about today, process areas obviously interact with each other. We have the subsequent stages, for example, in the FIBERLINE interacting with each other, and especially in the recovery cycle, where we have the very large degree of energy integration and material recycles. We obviously have a lot of interactions. And the thing to understand about the interactions is that even if we are optimizing the individual process areas to work as well as they can, the interactions can generate mill-wide bottlenecks for production and quality. And in the current world of pulp and paper, where we are increasingly striving towards greater autonomy in mill operations to get the potential benefits in production rates, quality, and cost, coordination of these individual process areas is necessary to achieve higher degree mill level targets. And our solution at Valmet for this coordination is the mill-wide optimization, MWO in short. It can be summarized quite nicely with this sentence up here. So mill-wide optimization is an online and dynamic solution for visualizing and optimizing the future mill state. What does it mean in practice? Instead of considering the individual process areas, we are optimizing the production targets of multiple process areas together, meaning that the decisions are coordinated to maximize profit, subject to quality and process stability. We can perform the optimization through two kind of main governing principles, which can also be combined in various application concepts of MWO. We can try to aim for maximum utilization of the mill production capacity, the installed capacity that we have, so pushing production towards the mill limits. And we can try to reduce the overall cost of quality, meaning we are trying to minimizing furnish, chemical and energy cost, maximizing chemical recovery, and so on. So the coordination is one thing. What does it mean more specifically? Mill-wide optimization at Valmet is based on flow sheet optimization, meaning that operating decisions are based on the total balance of the mill, the modeled total balance of the mill. And we are optimizing and forecasting the mill behavior for a defined optimization horizon in the future. Typically 2 to 5 days, but it is quite flexible. And one additional aspect that is important for mill-wide optimization, aside from coordination and optimization, is the visualization of not just the current mill state, but also the future mill state across the entire mill for all actors at the mill, which improves coordination between the departments. Final thing, the mill-wide optimization is a basic concept for performing mill-level process optimization. And depending on how we set up the flow sheet model and how we define the optimization problem, we have multiple application concepts that we can implement for various kinds of optimization scenarios. Today we are going to discuss the most kind of basic building block of higher level mill-wide or higher level and more complex mill-wide solutions, which is mill-wide production planning. And before we move on, just to give you an idea of where this kind of coordinating layer fits in a larger strategy towards autonomous operations in pulp and paper mills. So here on the x-axis, you can see the kind of conventional degrees of autonomy that are utilized quite commonly, starting from partially automated to fully autonomous. But we also believe that there's a y-axis to autonomy, where the foundation is formed from reliable and accurate analyzers, measurements, regulatory control, and so on. Then we have the individual optimization of each process area through APC, Advanced Process Control Solutions, and then this is where we come in as a coordinating layer for the optimized process areas, just beneath more longer-term optimization that is carried out, for example, in an MES system. Then some background in theory. I don't think I have time to go too deeply into this, but we can discuss also later if you have questions. So as I mentioned earlier, the MWO is based on the direct optimization of a process flow sheet model, a dynamic process flow sheet model, meaning that we model the mill as a flow sheet of connected process units and process inventories. And these process units and inventories contain the embedded process models for the relevant input-output relationships for the optimization problem. And once we have the flow sheet model set up and we identify the model parameters for the embedded models, we expose the equations we collect these equations and expose them all together simultaneously to a global optimization solver in an equation-oriented fashion. The mill-wide optimization platform, the core platform, is quite flexible and it readily supports both linear and nonlinear problems as well as continuous and discrete problems, depending on how we define it. The basic approach that we use is weighted single objective optimization, meaning that there's a single objective function value which consists of multiple terms that are weighted with the weighting factors. The main term is the profit terms, which essentially are derived from what the problem is that we are optimizing. Are we maximizing produced pulp, some quality KPIs, and so on. Then we have performance terms, for example, for tracking level targets or smoothing out production changes. And then we also have the option for optional penalty weights for implementing soft constraints. And in the online MWO application, we essentially take this flow sheet optimization concept and implement it in an online industrial mill setting. So we are continuously collecting data from the mill, which we're using to adapt the flow sheet model, as well as providing the initial states for the optimization. And then using the optimization solver and the optimization configuration that depends on the application, we are then optimizing the flow sheet model to generate the optimal process area targets and the predicted future production trajectories. There is also a planning mode for carrying out what-if type simulation scenarios. And in a commissioning and delivery project of mill-wide optimization at Valmet, our first step is to perform an offline mill-wide optimization audit, which at the same time is the stage of delivery where we set up the main framework of the application itself. So the purpose of the audit is to look at historical data from the mill and determine the benefit of or potential benefit of implementing the MWO. So we set up the optimization application and benchmark it against the historical data to find out what would have been in each situation the optimal way to run the mill. You can see a basic timeline of this audit procedure here, starting with data collection, flow sheet modeling, optimization problem setup, and then the actual analysis stage where we go through the data in short time increments and optimize and run the re-optimization of the historical data for each of those time increments. And when we aggregate the data from the analysis, we end up with the ranked a list of mill-wide bottlenecks at the pulp mill, for example, that we're going to talk about today, as well as the overall maximum improvement potential that we estimate from the data. And then onwards to the actual case study. So the online MWO solution was implemented for the first time and is currently running at an industrial scale market pulp mill producing multiple grades. You can see the basic project timeline of the commissioning here on the right-hand side. I won't go too deeply into that now, but you can get additional information from the paper as well. Important thing to note, the MWO is an open loop advisory system, meaning that there is no direct feedback, at least currently, to the control layers below. We are discussing the production planning functionality, meaning that the purpose of the solution is to optimize the current and future department-specific production rate trajectory. So what should the production rate be right now, and what should it be for the future horizon? And as we are talking about the production planning, we are mainly concerned with the mass and volume balance of the mill. There is a detailed user interface that we set up in Valmet DNA automation system, and consisting mainly of an overall flow sheet display for the mill operators to adjust future limitations, programming stops, and so on. You will see a picture of that later on. This is the basic optimization configuration. You can see the flow sheet model here on the right-hand side. In total, we are optimizing the production rates of 11 different departments in the fiber line and the recovery line. The optimization time horizon is 3 days, so we're predicting and optimizing 3 days into the future. And the application is running periodically every 30 minutes, but can be also launched on demand. The main objective is to maximize the produced pulp, subject to the mill bottlenecks, but we also have secondary targets for smoothing production rates, meaning that in an optimal trajectory, we shouldn't make too many changes in the production rate of the department to guarantee stable production. And whenever possible, we should also try to track inventory targets to their preferred target levels. The operator can adjust low and high limits of various departments, rate limits, how quickly you can make changes in the departments, and the optimization has to account for any discrete events that have been programmed by the mill personnel, mainly here stops and grade changes. And then a brief summary about the results. We will first look at the offline re-optimize the past audit results. In total, we analyzed 1 year's worth of data running in the 3-day optimization horizon time increments, containing various production scenarios, so the data was quite diverse. All in all, we identified a 4.5 maximum improvement potential for increased pulp production, and we obtained the list of ranked bottlenecks from which the cost desizing was the most significant bottleneck. And we reviewed the results with the mill, and they were quite convinced, so we decided to move on to the commissioning of the online application, which was carried out last autumn, so autumn last year, and has been running quite nicely at the mill ever since. We also had a kind of more intensive trial period where we benchmarked the outcomes of the optimization together and reviewed the results together with the mill. And based on this trial period, it was quite clear that the potential for improved production efficiency was demonstrated quite clearly. The overall impact for this trial period was an average of 5.2% increased production, resulting from both mill actions and from observing the mill-wide optimization results. In many cases, we could demonstrate how production increase would be possible based on the mill mass balance, so not considering, for example, quality, but purely based on the mass balance. And it was quite clear from the data that the mill was also able to consistently aim towards higher production rate targets at the cooking. The bottlenecks were logged and ranked for each month. You can see this ranking here on the right-hand side. The results largely corresponded with the audit results, although you could see some shifting in the bottlenecks, which I can discuss later. I'm not sure if I have time to do that here. The computational performance for the chosen time interval was extremely good. No problems there. We did encounter some challenges in the commissioning, but we were able to overcome those through application modifications and improvements. And in addition to the overall improvement potential, we also identified use case categories where mill-wide production planning proved to be particularly useful. The first category is about mill debottlenecking and balancing. So when we are running the mill nominally, how can we push production further by making like iterative tests that what is actually limiting the production. Then the coordination between the fiber line and the recovery line, quite an important topic at this reference site. For example, here we could see that the mill-wide optimization was proposing that the mass balance or the mill balance allows a roughly 2% increase in the production rate, but the mill actually in this situation failed to accurately implement the associated change in the evaporator feed rate that was suggested by the mill-wide optimization. And as the MWO predicted, the exact result that you can see here actually happened the next day. So in order to avoid weak black liquor overflow, they actually had to bring down the production again. And finally, the final use case category, which might be the most obvious one, is the planning and scheduling of both known and unknown, so unplanned mill maintenance and wash situations. You can see an example of that on my final slide. Full disclaimer, this is not the actual system. This is a comparable demo system for the mill-wide production planning. And you can see here that we have scheduled a scenario where the recovery boiler firing rate will be limited after 12 hours. And at the same time, we have maintenance action at the white liquor filter at the causticizing plant. And you can see from the different inventories here in the recovery line that we are able to manage this situation without major changes to the fiber line and no need to reduce the cooking rate. Conclusions: the optimization and coordination of mill departments to this kind of flow sheet optimization was proven that it can be used for both evaluating and realizing improved production potential at pulp mills. The technology utilized was proven as feasible in an industrial setting. The importance of visualizing the current and future state across the entire mill was demonstrated quite well, in our opinion. We also posit that this kind of mill-level coordination is an essential part towards more autonomous mill operations. And more specifically, production planning forms a basis for more detailed production optimization at the pulp mill. So with these words, I thank you for your kind attention. I hope I didn't spend too much time. If you have any questions, I will do my best to answer the questions. Thank you. Obrigado.
Let's move on to the second presentation of this session. Its subject is dissolved lignin carryover measurement in O2 and the zero stages brings opportunities for significant improvements in FIBERLINE operations. To present this subject, we have two persons. We have Caio Biondi. Caio Biondi is a Brazilian chemical engineer with a master in process optimization and over 10 years of diverse experience in the automation and advanced process controls implementation. Caio has made significant contributions to achieving business success through advanced process controls projects. He currently works for BTG as a senior process control engineer and data analyst, assisting clients in achieving success in their projects for the phase of study to the implementation. We have also Juan Pablo Pértega. He is an industrial engineer with a master's in business administration of technology industries, and with more than 15 years experience within the cellulose and paper industry. Juan has worked in the development and production area for pulp and paper companies. Since 2014, he works for BTG as Process Solution Sales Manager in Iberia, helping customers to rise their productivity. So, please, go ahead.
Thank you very much for your introduction, and I hope everybody can hear me. First of all, I apologize because the presentation should be made by our colleague Frida Eriksson, but she is sick, so I will try to do my best with my colleague Caio. So let's move to the presentation. We are talking today about the opportunities for improvements, for significant improvements in the FIBERLINE operation, thanks to the measurement of the lignin carryover, the dissolved lignin carryover in the O2 and D0 stage. So, starting with the bleaching process, the first the objective of the bleaching process is really achieve pulp production with optimum strength, brightness, and cleanliness. For this target, we have a sequence of bleaching with different chemical addition in order to rid off the lignin and brighten the pulp, and this means quite amount of cost in terms of chemicals, and this is something to consider, of course. A normal FIBERLINE control is based on the fiber kappa and pulp brightness. This is what we used to work in the last years, and this is the normal parameters to control. But it's true that the remaining dissolved lignin in the circuit has an impact and has an effect on the chemical consumptions, and especially could mean quite a big amount of the total lignin in the circuit. And more than this is the fact that the variability on the dissolved lignin is much higher than the variability of the fiber lignin, the lignin attached to the fiber. So this makes that the operator has to apply a large bias in order to compensate this variability, and without measuring it, you have to expend more chemicals to really control the bleaching process. So dissolved lignin, as Lord Kelvin said, to measure is to know. If you cannot measure, you cannot improve it, and this is the idea behind, to have in mind the total lignin content, which is the fiber lignin, what we can say is the fiber kappa, and the filtrate lignin or dissolved lignin, which is the filtrate kappa. So this dissolved lignin still remains after washing in the pulp, and also recirculation from different sources make contribution to this dissolved lignin in the circuit. As I mentioned, this consumes chemicals with, and the variability is quite high. The question is, can we use this information, the content of dissolved lignin, to dosage more accurately the chemicals in the bleaching stage? And we think so. You have here a trend in the inlet of the bleaching stage, in D0, with the measurement of the dissolved lignin, and in black dots the lab measurements. You can see the variability is high, and if we focus in a specific short period of time, we can see that between the lab measurements, we see that there is a lot of fluctuation in the dissolved lignin content, and this is what we see here also in the standard deviation. Even the average of the amount of filtrate kappa is lower. The standard deviation in absolute values is 1/3 of the fiber kappa, so meaning that the variability on the filtrate kappa is much higher than the fiber kappa, and it's something that we have to take into consideration. So the total lignin management is crucial in the beginning of the bleach sequence. We have see here different samples of different points or different moments, sorry. And you see that the difference on the aspect of the filtrate. And here we have in the trend, we have the value of the fiber kappa in blue and the filtrate kappa, which could mean, in sometimes you see here in the green, the percentage, and it can achieve the 40% of the total kappa, could be the filtrate kappa. So meaning that this is something really to have into account for the control of the bleaching sequence. And especially because this variability and also the reaction of the chemicals with the lignin, dissolved lignin, is quicker since they are more available in the solution. So from BTG, our concept is starting from the basics, which is the good measurement, to know the information, have good information, and with other tools, digital tools like visualization, analysis of data, this kind of study, previous study of the process, complete process, in order to identify where are the potentials and how much is the potential of savings, and then apply an advanced process control in order to improve the performance of the bleaching, and of course to save in chemicals, and finally autopilot the plant. So coming back to the basics, to the unit instruments, we have the possibility to measure the fiber kappa with hexavalonic acids. We have also the possibility to measure the total kappa, meaning the fiber mass plus filtrate kappa, and the filtrate kappa. And these are the tools, the instrumentation that we have in place for the bleaching optimization. How to use it? Mainly, we can use it in the O2 stage, but we are talking now about bleaching, and in the bleaching stage, we use the total kappa management, the total kappa value, as a feed-forward for controlling the D0. So meaning the bleach load transmitter is at the end what is giving us the information about what is the total lignin content in the inlet of the bleaching, in order to anticipate and to prepare the dosification of chemicals to optimize them. A modern bleach control, this is not easy to do just only with the instrument. You need some other tools that help to control the reaction times and things, and then is when the IPC control, advanced process control, enter in the equation, and also with the specific model predictive controls and multi-stage and multivariables process and controls. This is the way that we could get the most of this optimization. Now, my colleague Caio will continue with the presentation.
Hi everyone, I will take over from here to explain.
I'll take over from here to explain how these sensors are linked to the APC control strategy. So usually for max bleach, which is the BTG's solution for APC, uses the chemical usage as manipulated variables to control the main process variables of the bleaching process, which is mainly brightness and pH. We do that using many kinds of sensors. As Pablo said, one of the most important ones is the bleaching load transmitter, which measures the fiber kappa and the dissolved kappa. This one is very important because it says how much chemical we need to use in all the stages as a feed forward and also as a feedback. So you can use the measurement online from the D1 stage to fine tune the D0 stage and the opposite way. For the final brightness is also very important sensor because it's the main target of the bleaching. So the quality in the end is measured by the final brightness sensor. And also pH that are placed in many different places here in the line because it's important to the sodium hydroxide minimization in the bleaching. Talking a little bit about the bleaching cost optimization, we have this first graph here that has D1 brightness and total CO2 dosage. You can see here in this gray curve that you have a saturation after a certain point of dosage of CO2 in the D0 stage. So usually you have the D0 usage of CO2, and then this red line here is the D1 dosage of CO2. We have three different ways to optimize the bleaching plant. The first one is to balance the dosage between the D0 and D1 stage. This is because of this saturation here, so after a certain point you dosage a lot of CO2 but you don't have the final brightness increase as you expected. So we can transfer this CO2 dosage from the 0 stage to the D1 stage. And this is represented by pushing this red curve to the left until it reaches the green curve here. The second way to optimize the bleaching plant is to target shift the final brightness target. We can do that only if we reduce the variability, so we can shift to the left and stay within the normal distribution and guarantee that the quality parameters are being satisfied. So this is represented by pushing to the left from the green curve to the blue curve. The third way to optimize the bleaching plant is the sodium hydroxide optimization. We can do that looking for all the pH in the line and optimize its targets to minimize the sodium hydroxide dosage. Here is also important to say that not every bleaching plant is the same. So it's important to see if you have 1, 2, or 3 of these opportunities in this mill. So it's important to do a data analysis to see if we have the opportunity to cost optimization. This is why the normal savings vary in a wide range from 2 to 10 euros per ton of pulp. Some mills have more opportunities than the others, so this data analysis is very important to guarantee how much we can save here in chemical costs. It's also important that we do daily performance reports using our other tools to guarantee every day that we are delivering the savings that we expect to do. And to finish our presentation, we brought here 2 cases of bleach plant APC controls. One of them was in Brazil. We implemented 3 lines of bleaching in this client. In Brazil, it's a huge mill. This was a complete solution. We implemented the Max Bleach, the APC software, as well as different sensors for this line. We saved around 12% of chemical, CO2, and especially CO2 and sodium hydroxide that have a huge cost for the mill. And these represented $3 million per year for this mill. The second one was a Finland mill. This was different from the Brazilian one because we don't need to invest in instrumentation here. At that time, they already had a very good instrumentation, so we just needed to add 1 bleach load transmitter. So that goes through what I said, that every APC project is unique, and we need to see what we need to do in each mill. The results here were about the same range, from 11 to 17%, and the savings in euros was 4 euros per ton of savings. These were 2 examples, but in the past 5 years we implemented 22, or we are implementing currently 22 clients around the world, and yeah, that's what we got to first day. Thank you.
Thank you.
Okay, thank you very much for your presentations. And now we will open the discussion with the audience to place the questions to the presenters.
Thank you for both the presentations. I have a question, or 3 questions for the first presenter. So the first is about the digital twin. Does it allow to test different scenarios and see how the 3-day forecast goes? And so
Yes.
this allows for this testing scenarios?
Yes,
Okay.
you can use the planning mode for that purpose. So you can change different settings in the optimization, test different process conditions, and rerun the problem essentially.
Thank you. So the other question is, how does it interact with the process? So is this like a recommendation system, or does it, so it does not set points to the controller?
No, there's no direct feedback at the moment. It's an open loop advisory system, so it gives the recommendations for the production trajectory, as well as what should the first kind of target, like first set point be, to start like moving along that trajectory, but it's still the responsibility of production management and the operators to actually implement the values. I had it on the conclusion slide that in the long run, we are aiming at someday in the whole strategy of mill autonomy, we are aiming at having the feedback connection at least to some degree, but at least for the moment, we are dealing with open loop advisory.
So the last question is, how does the flow sheet optimization compares, or what makes it different from like existing software like Aspen flow sheet optimization?
Yeah, that's a very good question. So first of all, so comparing to like commercial simulation software like Aspen, we are first of all running it online, which I guess you could do that with Aspen solution as well. But it is also, I have to confess, I'm not entirely familiar with what the basic core of the Aspen flowsheet optimization is, so I can't give you a more exact answer on that, unfortunately. But I don't know, for example, if Aspen's solution is this equation-oriented approach, where you essentially from the flow sheet, you convert the flow sheet into the equation set, which is then solved globally by the optimization solver. Or is it kind of this, what's the other approach, this sequential type of optimization?
I think they have both.
Oh, okay.
Yeah, it's possible,
Yeah.
because the globally it's more
Yeah.
computationally expensive, so you can have both.
Yeah, I would need to go into the specifications to a greater detail. I don't want to be guessing and giving wrong information now, but I can look it up and I can get back to you on that.
Okay. Thank you for answering, and good work.
Thank you.
I have a question that can be for each one of you.
Okay.
This process is on the stock world, and I believe it's a trend. But I have an headache. That is, when everything goes well, it works perfectly. When everything goes wrong, who will manage the mill? If the know-how will be lost, and operators and people is a concern, and the know-how will be lost with this kind of process, how do you see the trend, or how do you see the future for that?
Was the question for both of us, or Okay, so that is actually, I didn't highlight that too much in the presentation, but that is actually one of the kind of core reasons why we put such a great deal of interest in the whole aspect of autonomy. This kind of mill-wide optimization approach really is a tool for the operators and the mill personnel to realize their full potential, to interact with each other, to transfer information from one generation of personnel to the other, to the next. So, as we all know, the people who have been working at the mills for a really long time will soon be retired, and some of that know-how will be lost. And that is where our digital solutions come in, to provide the new mill personnel with the assistance that they need. So that is very much at the heart of what we do. Hopefully I was able to answer your question, at least from my side. Okay.
My question is that, but is a little bit more, is the full autonomous operations will be soon will appear.
It is.
It's like
It is the main kind of development that is going on at the moment. Yes, yeah. But of course, like autonomy, as we looked at in the main strategy, consists of many different components. And we really see it in such a way that it is really kind of a building that you start from the foundation. You need to have a solid foundation. Then you go to the individual process stages. Mill-wide optimization does not essentially require you to have an APC layer, but if you get the targets from the upper level, it will then be the responsibility of the operators to make sure that we're actually reaching those targets.
My question was, the root of my question was, do you have something that can compensate this autonomy for the operators, for the people that are managing the mills? Because you will have data scientists and you will have IT people that will replace all traditional operators.
Yeah, well, one, yes. Okay, please. Sorry, I didn't mean to interrupt.
Sometimes the things happen.
Yeah.
I wouldn't like that they didn't, but they do.
Sure.
And in those cases, how do you compensate this? How do you trade off this no loss with this new technology of autonomy?
Hopefully I'm not skirting around the issue again, but as we have seen quite clearly in the media as well, the whole AI side of things is also rapidly entering into our field of industry and our everyday life. And that of course is also a great opportunity. It's not specifically a part of the mill-wide optimization because it is the job of it is to coordinate the different departments. But this kind of AI co-pilot functionality is something that at least I personally see could be a part of the future in data.
Just one comment about this. Also from our perspective, this is not yet done, this step, and it's an opportunity also for the operators with an advanced process control to really get more knowledge, and is really to share. So it could be an opportunity. Of course, we are not thinking into replacing the operators right now because they are really necessary, and of course, it's an opportunity for learning more. And of course, there are moments where the APC has to be disconnected, probably, because there are some issues, some problems, and it could happen. And I don't see losing the information so fast in the operators right now. So I think it could be an opportunity also for improving the knowledge.
I absolutely agree, and I would also like to add to that at least our view in the MWO development is really about empowering the operator, to providing operators with more tools for really realizing the maximal production that can be achieved, keep quality on track, manage situations that they might not be used to, and so on. So that is really at the core of what we do. So I couldn't agree more with your statement.
I'm sorry, but I will insist on the theme because I think it's very interesting. And complementing what Paulo just asked, I'm curious about what happens when you start a new a new line or you change completely a line, and you are completely dependent on these models, because the models, they learned with the data that you teach them, but suddenly you have a big change on the mill and you have to teach them again. So how are you doing it now, and how you are planning to do it in the future? And this crosses with what Paul says, because if knowledge starts to be scarce on the mills, we will have less and less capability of reacting to these changes.
From BTG point of view, the training is really a very important part of the process of the project. So for us, it's really something that the training is absolutely essential for the project, and also the communication between the supplier and the producer. So it's something that we cannot miss, and of course we have to spend a lot of time in training operators to understand, and it's a tool that will not solve everything. The thing is that the customer, the operator, cannot be looking at the trends, many trends for many variables 24 hours and taking care of. It's a help. So okay, if you, I don't know if I get the question right, but if you change completely the process and there is a change, we have to make a plan or a training also for the operators to understand how the system will act. And this is part of the project implementation in our case.
And also comment on that. So yeah, so that is a very relevant question. So if there is a major change in the process that completely changes so we actually are talking about the rebuild, then obviously we can use existing models as a basis, but obviously we would then need to review the models so that they are still valid and applicable. Most likely they're not, they need to be updated. And that really places importance on the monitoring of the models in the daily operations, even when we are not really expecting that there has been any changes. We do have like monitoring of the models. We are monitoring how the different adaptation coefficients are behaving and making deductions based on that, on what the condition of the models is. We are adapting the models or the production models, these basic production models that we have in the production planning based on data from the mill. Of course, we could do more. The adaptation approach that we currently have, this kind of feedback style adaptation, is still relatively straightforward and could be more extensive and could be improved further, or will be improved further in the future. But I think it's a very relevant question. The continuous monitoring and adaptation, online adaptation of models in these kinds of applications is important, and you need to have a strategy. If you know that there's a big change in the process that completely changes the behavior of the process, you need to have strategy, you need to have cooperation with the customer, that you have a plan for updating the models and training any changed behavior to the operators as well.
Thank you.
Any other? We are just on time. Maybe one more allowed, if any.
I have one more here. So for everyone, so first of all, thanks for the presentation. I would like to hear from you regarding, we all agree with the technology advances and the autonomous operations. I understand that everybody in this room is in favor of that. But in a time perspective, two questions. First one, how you see the marketing accepting it and implementing it? And the second one, how close are we from autonomous mills? If you can say year, months, that would be my two last questions.
The first one, sorry, the first one was
The market,
market, okay.
how you see the
No, I think
overall
that
market?
in the past it was more reluctant to this kind of solutions. I saw that it takes time to develop. We have this technology from several years ago, and what we see is that now the customers start to realize that there is the way to do it. So I have the feeling that these doubts start to disappear, and the customers start to think that this is the way. So I would say that it is changing this mind in the customer. Regarding the second one, when I cannot, I will not answer on this because honestly I don't know. It's the way, but I think it's not very short. But it's my guess. I really cannot say.
Yes, I very much agree. I think that, of course, it's a very old business. It's a very established business. For example, in the Nordic countries, in Finland, where I'm from, the pulp and paper industry has been around for a really long time. You have people who running the mill who really know what they're doing. But I think the customers are starting to really see the benefit of moving in this direction. It also ties together with the previous discussion that we had about the aging workforce at the mill. If you take, for example, a mill operator that has been running the mill for like evaporators for 30 years, and there is a change in cooking, he probably knows, like, whether he implements it or not, but he knows, he or she knows how you should run the evaporators, at least like roughly, or on like an instinctual level, they know how to run. But when you get the new workforce, they really start also seeing the benefits of having these kinds of tools, that when the fiber line production changes like this, you should adjust the recovery line like that. So I think that I very much agree with the previous statement that you start to see a change in trends. I'm also not going to make a guess, unfortunately, skirting around the issue, but I don't think I'm qualified to make a guess of a general timeline. Also because there are differences between different customers and different mills as well. We are progressing in the correct direction, but this kind of strategy and timeline that I showed you, you have to also understand that it is a long-term development, so it will take time, I'm sure.
Thank you all.
Well, we are also running out of time, so I would like to thank everybody for the participation, especially for our panelists. And we close the session now. Thank you very much. Remember that 2:30 the buses are leaving, and we are now going for lunch. The rest of it. Thank you very much.